Yeah, so today we're going to go through the moment of inertia of some objects. So you should be sort of familiar with this from physics, but we'll go through it again. So we're going to go through examples in 1 dimension, 2 dimension, and 3 dimension. Okay, so let's start with moments of inertia in 1 dimension. So let's say we have a metal rod or something like this. Yeah. So it's like a metal rod, but the idea is that it's very thin but quite long. So it's approximately one-dimensional. Yeah. So the radius is very small, but the length is very large. So what we want to do is imagine rotating this around the XY plane. Okay, we rotate it around about some axis that we draw. So let's say that the axis is right through the middle. And we're going to rotate this around. Now, rotating it around requires some force, right? And if it's rotational, we call it torque, not force. But we rotate this around, and what we want to work out is how difficult will this be to rotate? Okay. Now, depending on where the axis is, it will change the distribution of mass, okay, on either side of the axis. We see when it's right through the middle, on both sides, it's the same amount of mass being rotated around. Does everyone see that? Okay, so it's right through the middle. On this one side and on the other side, it's the same amount of mass being rotated around. Okay. Now, if we have another picture like this, if we have the axis down the one side like this here, we see that it's going to be a little bit different. So over here, there's more mass away from the axis than in the first case. Okay, so in the first case, the mass is very close to the axis because it's symmetric on either side. This one, you see the mass is very far from the axis. Okay, now just thinking about, everyday experience and stuff, which one would be more difficult to rotate around? The one where the mass is closer or the one where the mass is further away? Okay, so just think about it. So we have these two options. One of them will be more difficult to rotate. The mass closer or the mass further away? You say further away. Okay. How many say when it's further away? Okay, hands up if you'd say further away. Okay. Hands up if you say if the mass is closer. Okay, no, good. Okay, so keep that in mind. So we're going to do the calculation and then we'll see which one's actually easier. Okay, so firstly, how do we define the moment of inertia? So we're going to look at a very simple case of just orbits, okay, looking at something orbiting, and then we'll generalize it to this case here. Okay, so let's say we've got our axis, and then at some distance r away, we've got a mass, let's call it m, and it's being rotated around. The way we define the moment of inertia, or how difficult is it to make the object go around the axis, is given by the following. Okay. So it depends on the radius, okay, and it depends on the mass, okay, how difficult it is to rotate around. Okay, now this is just for a single mass going around. What we're going to do now is generalize this, like we did yesterday, for not a single mass, but a bunch of little masses along the rod. Okay, so let's generalize this. To a 1D rod. Yeah. So let's have a look at this picture again. So we'll look at this first picture. So we've got our metal rod or something like that. Okay, we rotate it around an axis. Now we're going to imagine cutting it up into little pieces exactly like we did yesterday. So we cut it up into little bits. Each of these little bits has a mass dm, again, like we did yesterday. And then each of these is going to have some distance from this axis. Okay. So we can think about it in terms of this previous picture, where we have a single mass m being rotated around. But now instead of a single mass, we have a bunch of little masses df all along the rod, and each of them is being rotated around. So they each have their radius, they each have their mass, and it's going to go around. Now, instead of adding up the masses, right, these are infinitesimal. We don't add them, we integrate them. So here we have the integral r squared dm. Okay. So again, very similar to this previous one. So for a single mass, it's r squared m. But if you have a bunch of little masses, it's not m, it's dm for the little mass. And we have to add it all up. So it becomes I equals the integral of r squared dm. Okay, that's the general formula that we're going to be using. Okay. Now let's apply this to the one-dimensional case. Exactly the same idea as what we did last time, when we had the density times the volume gives you the mass. We're going to have a very similar thing here. Now, it's not going to be the volume density, because this is one-dimensional. It's going to be the line density or the linear density. Have you heard that before? Linear density? Or like if you have charges on a line, it's the linear charge density. You've heard that? Okay, same idea. But instead of charges along a line, it's now mass along a line. Okay, so we define the linear mass density. We call it lambda. So lambda of x, because it might change along the length of the rod, the density might change, is going to be dm by dx. Okay, so this dm by dx is the linear mass density. It tells us how the mass changes as we move along the rod. So one side could have a high density, one side could have a low density. That's given by this lambda over here. Okay, we can do a little bit of rearranging. So we can take the dx over to the other side, and we get dm is going to be lambda dx. Okay, so we have the linear mass density times the length. That gives us the mass back. Okay, so in one dimension, we can write this as I is equal to the integral from a to b. So the start of the rod to the end of the rod. Then we still have this r squared, because it's orbiting around, so we have r squared. And then instead of dm, we have this lambda x dx. Okay. Again, this whole part here, this bit here, that is our dm from the original formula. Okay, any questions so far? All good. Okay, so let's have a look at these two cases again. So we're going to have case number 1, case number 2. Okay, and again, remember what you said, which one's more difficult. So let's look at number 1. So we assume a constant density, let's say metal rod. So it's all the same material, same density throughout. Metal rod. With the axis through the center. Yeah, so it's the same setup as we have for that first picture. Okay, so let's set up our coordinate system so we can put some numbers down. So let's have xy, and we got the rod along the x-axis here. And we rotate it around y. Yeah, you can pick different axes if you want x and z, whatever you pick, as long as we can put some numbers down. So this is through the center. So let's say that the rod has length L, the total length L. So if it's through the middle, we can choose that to be the origin through the middle there. So on the one side, it's going to be minus L over 2. And on the other side will be L over 2 because it's through the middle. Okay. So we've got that for our picture. Now let's just pick one point to be our little mass piece dm. And then we're going to figure out what this radius is going to be. So we just color in a little block dm, and we can see that the radius is from the axis to the little mass piece. So here's our axis. From the axis to our little mass piece, what will the radius be? From here to here, what's that length? X, yeah, the radius will be x. Yeah. So for any mass piece that we pick along the rod, the radius is just x. Okay, so we have everything we need now. So let's substitute in and work out the moments of inertia. So we need to integrate over the length of the rod. So it will be from minus L over 2 to L over 2. The radius we said was x from our diagram. So we need radius squared, so that will be x squared. Times, and now we need the linear mass density, right? The lambda. So if we go back up here, the lambda was dm by dx. Okay, but here it's constant, so it's not dm by dx, it's just m over the length, okay, because it's constant. So let's say that the total mass is m. The length of this we said was L, so the density is just m over L. Okay, this is constant density. Yeah. So it's very similar to what we did last time. So you cut up your object into the little pieces, you work out whatever the radius needs to be, the density, and then you substitute. So m over L, that's a constant, we can take it out. Okay, so we just have x squared dx, that's easy to do. Okay, so we get m over L, and then we end up with twice this, so 2 over 3. We can simplify this a little bit. So at the bottom, we have 2 cubed. We've got a 2 at the top, so there'll be 4 at the bottom. And then times the 3, so there'll be 1 over 12. And then L cubed over L, that will be L squared. So we have 1 over 12 mL squared. Okay, so keep that in mind. This is the moment of inertia where the axis is through the middle. Okay. It's how difficult it is to rotate around. The larger the number, the more difficult it is to rotate. Okay, so that's for the case 1. Let's set up the integral for case 2, and then we can compare. Okay, so case 2, we have the same sort of thing. So let's just copy this over. Okay, but it's not through the center, it's through one of the ends. Through the end of the rod. Okay, so let's set up our coordinate system so we can put some numbers down. So it's going to be something like this. So 0, the rod has length L, so that endpoint there will be L. So X, Y, we rotate around. Same idea as before, we're going to pick a little mass piece, see what the radius is, and then substitute. So here we got a little bit over there. Okay, remember the radius is from the axis. So from the axis to our little mass piece there, that's going to be x. Okay, and then we have everything we need. So I is going to be the integral from 0 to L. So from the start of the rod to the end of the rod. The radius is x, like we have over there. And then the density, it has mass m, length L, so the density is m over L dx. Okay. So same idea as before. M over L is a constant. We can take that out. So we have m over L, 1/3 x cubed. Yeah, so we have 1/3 m L cubed over L, so L squared. Okay. So we have this. Okay, so between the two of them, we have case 1 where it's through the middle, case 2 where it's through the end of the rod. Which one's more difficult? Number 1 or number 2? Number 2. Yeah, 1/3. It's bigger. Okay, so this one is more difficult. Why is it more difficult? It's because more of the mass is further away. Okay. So if we go back to our original equation we had here, I equals r squared dm. So here it's proportional to r squared. So if more of the mass is further away, this is larger. Yeah. In the other case, we had more of the mass closer. So r is smaller. Okay, then it will give you a smaller moment of inertia. Okay, so more mass distributed further away, we expect a larger moment of inertia. Okay, any questions about these two examples? Okay, so then the third one you're going to do for homework. Find the moments of inertia for the 1D rod if the axis is 1/3 into the rod. Okay, so we looked at the axis halfway, we looked at the axis all the way at the end. Now what happens when it's 1/3? So we'll draw a little picture. Okay, so we had the axis at the start there, we had the axis in the middle. Now what happens if it's somewhere in between? Okay, so now it's a little bit different because over here, when you rotate this around, you've got some mass being close and a lot of mass being further away. Okay, so you need to think about what happens there. We got some mass close, some mass further away. So we expect it to be somewhere in between the two cases. Okay. The axis is not quite at the end, but not quite in the middle. So you should get a number somewhere in between the two. Is that clear? Okay. Any questions for this homework? And then number 4. Find the moment of inertia for the metal rod with density lambda of x is x1 minus x and length 1. where the axis is at position A. Okay, and A is somewhere between 0 and 1. Okay, so we've got a rod, length 1, but a non-uniform density. Okay, so here the density changes when you go from one end to the other. The axis is going to be at some A, and we don't know what it is. Find the moment of inertia for that. Okay, so if you can do number 3, then number 4 is very easy to do. Right. Any questions for this number 4? Oh, okay. Any issues before we move on? All good. Okay, now let's have a look at the 2D case. We won't look at the general 2D case. You'll cover that in the MATH162. I don't want to spoil anything for that. We're going to look at very simple situations where it's just a disk. Okay. So I just put a note here. This is just the special case for a disk. Okay. The other cases for like squares and triangles and all that other stuff, you'll cover that later. Okay. We're not going to go through that. Now, that doesn't mean it's super easy. It might still be an inhomogeneous disk, okay, but the shape is going to be very simple. Okay, so let's set up a picture and then we can work it out. Okay, so we've got ourselves a disk. So it has a very small thickness to it, so it's very, very flat disk, but the radius is going to be quite large. Okay, so it's approximately 2D. Okay, so it's very wide, but very, very thin. The axis for this will always be through the center. Okay, we're not going to do any offset axes for this 2D case, but for the 1D case, right, it'll be something like that. Okay, where the axis is off center. But for 2D, it's always through the middle. Okay, so we've got the axis through the middle there, and we're going to rotate this around the axis. Okay. Now, the formula is the same. I equals the integral of r squared dm, but that dm will change, again, depending on the situation. So we have I equals the integral r squared dm. So same formula for all of the cases. It's just this dm changes here. Okay. Now, in the one-dimensional case, we replaced this dm with the linear density times the length. In the two-dimensional case, we're going to replace the dm with the two-dimensional density times the area. Okay. So here in 2 dimensions, the area density is given by, we call it sigma, and it might depend on the radius. So from the center of the disk going outwards, the density can change depending on the radius. So at the center of the disk, it might have some density. As you move out to the end of the disk, it could have some other density. Okay, so it depends on the radius going outwards. Okay, this is defined as dm by dA. So the change in mass over the area, because it's 2D, it needs to be the area. So we'll do a little bit of rearranging. So we get dm is going to be sigma of r dA. Yep. Now, what we need to figure out is this dA here. What's the area dA? Okay, so since we're working in the special case with the disk, we know that the total area there is always a circle. Okay, so we can use that to help us out. So let's look at this disk from the top now. So we got from the top there, and we have our center point, and we're looking for the little dA. Now, there's a few ways to do this. We're going to look at the very simple case. There's more complicated ways using polar coordinates. We're not going to do that. Okay, you'll cover that later. So here we're going to imagine this dA as a little ring going around. Like that. At some radius r. Okay, so we're going to have these concentric rings going around, very similar to the shell method that we used. So right at the center here, this ring is going to be very small. It's going to have some area in pink. And as we go outwards, this ring will have larger and larger radius. Okay. And if we add up all of the rings from the center bit to the outer bit here, that covers the full area. Does everyone see that? So what is the area of this pink ring over here? Well, it's got a radius r, and it's got a little width to it, dr. So the area of the pink ring, dA, is going to be the circumference of the circle times the little width. Yeah. Is that clear? Clear? Okay. If you ever forget this, just think back to what we did last year. What's the area of a circle? Pi r squared. What's the differential for this? 2 pi r dr. That gives us an idea. Okay, so if you ever forget, just go back to what we did last year. dA is 2 pi r dr. Okay, if you ever forget. So you can think about it in terms of the picture, or you can do the differential like this. Okay, you get the system. Okay, so let's substitute everything in and get our formula. So the moment of inertia I will be the integral. We're going over the radius, so it will be from the center of the circle that has radius 0 to the outside of our disk there, outside of the circle that has radius, let's call it capital R. Okay, so we've got the bounds now. Then we need the radius squared. Okay, that's just from the formula. Then we need dm over there. And we see dm was sigma of r dA, and A is all of this. So we're just putting everything together. Okay, so there's 3 parts to this. So this bit. Okay. So we have the r squared from the moments of inertia formula. Sigma, that's the density. 2 pi r dr, that was our dA. And we put it all together. Okay, now we can simplify this a bit. 2 pi, that's a constant. We can take it out. And we've got r and r squared. That'll be r cubed. So we can write it like that. So given some disk with mass density sigma, we can work out the moments of inertia. Yeah. So let's have a look at an example. Also, you don't need to memorize these formulas. Okay, they will be provided. Okay. So the disk method, washer method, shell method, I'll give you those formulas. And then these ones that we've got here. Okay, I'll give you those formulas. Now, you might still be asked, derive the formula, but this end result here, this will be given. Okay, Okay, example. Find the moments of inertia for a uniform solid disk. Okay, so very easy question. Okay, so we know it's a uniform solid disk. So whenever you see uniform, that means constant density. And it's a disk, so we got our formula that we can use. So let's work this out. So we integrate from the center of the disk to the outside of the disk, so from 0 to r. Then we've got 2 pi. Now, sigma, that's the mass density. That is the mass over the area. So let's say it has mass m. What will the area be? It's got radius capital R, just pi r squared. Yep. Okay, so that's the sigma part done. And then we still need that r cubed dr. Yeah. All of that stuff in front there, that's a constant. We can take all of that out. So the powers will cancel. So we have 2m over r squared. Okay, so 2 over m over r squared. 1/4 r to the 4. Okay, so we've got a quarter we can take out. So 2 over 4, there'll be a half on the outside. Then we've got m. And then r to the 4 and r squared, we're left with r squared. Okay, so that will be the moments of inertia for just a simple solid disk. Okay, we have that. Okay, so now for example 2, we're going to look at something very similar, but the idea is the same as we did last time, where the mass is distributed more to the center or more outside. Okay, we're going to look at that case. Okay, so for example 2, you're going to finish that for homework. So we're going to have our disk as normal. But now the mass distribution is not going to be constant like we had before. What we're going to have here is more of the mass on the inside and less of the mass outside. Okay, so it's more concentrated to the center. And what you're going to figure out is it easier to rotate this disk compared to uniform? So either the mass is flatly distributed or more to the center. Which one will be more difficult? Okay, think about it. So flatly distributed, all of the mass is even, versus this case here, where the mass is more concentrated to the center. So it will be like this. Yeah. So we have e to the minus r squared. That's going to be how it's distributed. So we see that when r is small, we're going to have a lot of mass there. But as this r gets larger, this sigma gets smaller. Okay. So it means more of the mass is towards the center over there. Okay. So just have a guess which one will be easier. Okay, mass in the middle or mass out towards the end. Okay, and then try that for homework. See if your guess is right. Right. Any questions for this homework? All good. Okay. Then the last thing for today, the 3D case. Same idea, same formula. We're just changing up whatever that dm is. So this is going to be, again, very similar to what we had last time. So same formula as before. So let's just draw a picture first, and then we'll put the formula. Okay, we'll start off very simple, like we did last time. So we've got a solid cylinder, and we're going to rotate it through the center. Okay, so rotate through the center there. And we want to work out what is the moment of inertia for the shape. Okay, so we have our formula from before. Okay, something like that. And we want to rewrite this formula for these cases. Okay, like we did for the 1D case, the 2D case, and now for the 3D case. Now, this dm is going to be a little bit different, okay, because it's now in 3D. So we have the same idea as before. We pick a little cube, dm. So we cut up our shape into a lot of little cubes, dm. This little cube dm is going to be some distance from the axis. Some distance r. And it's going to go around the axis, okay, like we had before. So this dm over here, that's this little dm over there. And we're going to do this for all of the little mass pieces, integrate it up, and that will be the moment of inertia. Okay. Now in 1D, we had the linear mass density, dm over dx. For 2D, we had the 2D mass density, dm over dA. In 3D, it will be dm over dv, like we did yesterday. So in 3D, we have the volume mass density. We call that rho, like we had last time. And like we had last time, it depends on where you are. Okay, it could be different throughout the shape. So rho x, y, z. Okay, so it depends where you are in the shape there. And this is going to be dm by dv. Yeah. A little bit of rearranging like we did a little bit ago. So dv we can take over to the other side, and we can find dm, which we need there. Yeah, so dm is rho dv. Let's substitute it into our equation above. Okay, we end up with this. Now, depending on the density, depending on the shape, this dv over here will either be the dv from the disk method, the dv from the washer method, or from the shell method. Yeah, it depends on the situation. Is that clear? So same as what we did yesterday. So dv, if we're stacking vertically, we use the disk method. If we have concentric shells, we use the shell method. It depends on the situation. Okay, let's work it out for what we have here. So we've got a cylinder. And notice we're interested in this radius going out, right? Because each of these masses will be going around, that's your hint, around the axis with some radius. So which method should we use? Shell, exactly. Right, because we're going to have the mass going around in a radius. If the little dm goes around in a circle for this 3D shape, it makes a shell. Okay, so we're going to use the shell method. So we have r is equal to the integral. So the shell method goes from the center of the shape to the outside of the shape. So it will be from 0 to r squared. The density, that will be the mass over the volume, right? So the mass of the cylinder, let's call it M. What's the volume of the cylinder going to be? The cylinder? I'm hearing someone say 3. Yeah. Volume, pi r squared h. Okay. So mass over volume, that's our density rho. Okay. Next, we need the dV from the shell method. What is that? Check your notes. dV for the shell method. It's just from yesterday when we did the center of mass and total mass, all of that. Uh, 2 pi r. Yeah, and then the h, what will that be? The height of the function here. It's just the height of the cylinder. H. Okay. Does everyone see that? So 2 pi r, that's the circumference of the cylinder, and the height of the cylinder is h. Does everyone see that? Okay. Okay, so everything subbed in. Let's take the constants out. 2m we can take out. Okay, pi at the top, pi at the bottom, that's going to cancel. H at the top, h at the bottom, that's going to cancel. Okay, interesting. It doesn't depend on the height. Okay, so h cancels. And then we still have the r squared at the bottom. Okay, so very interesting. This h and the h cancels. So it doesn't matter how tall the cylinder is, it will have the same moment of inertia. Okay, you can think about that. Why is that the case? Okay, that's more of like a physics thing. I'm not going to ask you on that, but think about it. Okay, from 0 to r. What are we left with? R squared, another r, so r cubed. So we have 2m over r squared, 1/4 r to the 4. So we have 1/2 m r squared. And this looks very familiar. Okay, we go back a little bit. It's the same thing we got for the disk, because we showed now it doesn't depend on the height. So you've got a very small disk, you get this moment of inertia. What do we call a very large disk? Cylinder. It has the same moment of inertia. Yeah, so again, just think about why that's the case. So here this is independence of height. Maybe I can put that as like a bonus question for the next quiz. Yeah, explain why it's independent of height. All right. Any questions for this one? Okay. Okay. And then just one more homework problem for today. Find the moment of inertia for a uniform solid cone. With base radius r and height h. Well, mass m, but that's height h and mass m. Okay. Okay, so find the moment of inertia of the shape. Now, what I suggest you do on Wikipedia, there's a nice page with a whole list of moments of inertias for different shapes. There's cubes and cylinders and donuts and all of that. So it's got the shapes, and then the next column, it's got the moments of inertia. I suggest you go through that list and set up your own integral to calculate that. Okay. So check there's pyramids and all sorts of shapes. So you try work it out and then compare with that list. So we've done the first two here. So the cylinder, that's the first one. The cone, you're going to finish that off for the second one. There's a few more. Okay. So set up the integrals, try calculate it, and compare with that list. Okay. So there's cylinders, there's cubes, and there's donuts. There's a bunch of shapes. Okay, you can do that for some practice. So for tests and exams, I'm not going to give you some very funny shape. It's going to be something simple like this. Okay, so maybe pyramid, cone, cylinder, that donut shape. Okay, something quite simple. All right. Any questions for this one? Okay, good. So next week we're going to do the last bit of work for the semester. So we're going to go through space curves. So curves in 3D. We're going to look at the lengths of the curves, tangents, normals, binormals of the curve. That will be important for mechanical engineers. Tangents, normals, binormals. You do a lot of that later on. And then after that, we're going to look at the surface area of shapes. So we've done volumes, we've done moments of inertia, we've done total mass, all of that. The last thing is the surface area. Yeah. And then that will be it for the class test 2. And that will be the same for the June exam, June test. Yeah. Any questions for the work next week? Okay. Yeah. And then please remember